All right, good afternoon. Today we are gonna talk about free vibration with damping. When we have damping on our mass spring, how the response of the system is going to look like. Any question before we start? All right. So what we studied so far, we had mass and spring with the stiffness of K and mass with the M. So when we move the mass, the system from relaxed or equilibrium position by x naught, and then we release that, it's gonna start oscillating. We could derive the equation of motion for this system as mx double dot plus kx equals to 0. And now this system we are gonna add a damper. So we would like to derive the equation of motion and then find the response of the system. So before we do that, we need to know how the damper is working. So on spring, when you make a deflection on the spring, it's going to apply force in the opposite direction of deflection. So if you have if it's at the L naught, if you make deflection with the magnitude of x naught from the relaxed point, then at this end you are going to apply force in the opposite direction of deflection. We extended the spring with the magnitude of kx naught. Let me change it to x. Kx. So this is how the spring is working. The damper is gonna be against the motion. So in a spring, the force was a linear function of deflection. In damper, it's gonna be, if I have a damper, it's gonna be a function of velocity, x dot. So if this system is moving in the right side, the damper is gonna apply the force in the opposite direction of motion. So if the system is moving in right side, the force applied from the damper is going to be in the opposite direction. So the damper is against the motion. And how much would be the force? The force is changing with velocity in a term of constant coefficient that we call it damper or damping coefficient. So the force is gonna be negative c x dot due to the damper. This side is the negative. And for a system like this, when it's at the distance of x, if I want to draw the free body diagram, I have mass. Due to the spring, we are going to have deflection of x. So we are going to have the force of kx to the left side. And due to the damper, we are going to have cx dot to the left. And c is the damping coefficient. So, and the summation of the force is equals to mass times acceleration, which is mx double. So the new governing equation or equation of motion is gonna look like this. Mx double dot plus Cx dot plus Kx equals to 0. So we have one extra term which is coming from damping. So if this is the relaxed position, L naught, if I move the system from the M naught by the X naught and keep this mass here before I release that, if I want to draw the free body diagram, what would be the force applied to that? One force due to the deflection on the spring, K times X naught. How much will be the force due to the damping? What will be the force due to the damping? If I move this mass from the relaxed position by X naught and keep it here before I release that. Say it again. What would be the velocity at this point? 0. I'll keep it here. So there is no force applied to the mass due to the damping, just at this position. After I release that, it's gonna start oscillating, so the mass is gonna have the speed. So when it's moving in this direction, it's moving to the left, so the damping is gonna apply the force in the opposite direction. Make sense? And when this mass is touching this position, just this position, it's gonna have the speed, but the force due to the deflection is gonna be 0, but we have Cx dot, which is the maximum speed of the mass on the motion. So the mass is gonna see the maximum speed, which is going in the opposite direction of the motion. So at this location, at this position, there is no force coming from the spring. At the other extreme position, there is no force coming to the damping. So no matter how much deflection you have on your system, the damping is just against the motion. So if it's moving, it's active. Make sense? And it's wasting the energy of the system. So if I have something like this, if I ask you if this is the x, if this is time, if I ask you to draw the response of the system, the response of this system is going to look like this, for example. A cosine of theta omega t minus phi naught, or phi. So it's going to look like this. It's starting from one point, it's going to repeat itself, because we don't lose any energy. But when we have damping, this term, it's going to dissipate the energy. So it's going to look like, we are going to talk about that shortly, but it's going to look like this for some value of the C. As you see, the motion is going to start at very high peak, but the peak is going to decreasing, and after a while, the motion is going to die. So, depending on the value of the C, the motion can look like this. But the point is, the system is going to lose its energy over the time because we are losing the energy. Make sense? All right. The next step is we are gonna find the response of this system. But before we start finding or working on the response of this system, let me work on some examples to see how you can derive the equation of motion for a given system. Alright, suppose we have a spring with a stiffness of K. Is connected to this cylinder, which has been we are gonna have pure rolling, so no sliding, so pure. This cylinder is gonna have the radius of the R. We are gonna move it. We are gonna move the system from equilibrium position, then release that. Since you made some deflection of spring, it's gonna push the cylinder back, so it's gonna start oscillating, and we assume that we have pure rolling. We would like to derive the equation of motion for this system. We are gonna find the equation of motion by Newton method and energy method. Then I'm gonna add one damper with a coefficient of C to this system, and then I'm gonna derive the equation one more time. So let me start with Newton method. Which force is making this rotation happen? If I just rotate this, which force is gonna make this rotation happen? If we assume that we have pure rolling, what is making happen? Say it again. K. What do you mean by Ks? The friction. If we don't have friction, you cannot have pure rolling. You remember this from the diagram. If there is no friction here, it's gonna start sliding. So if I draw, so you move it by the x, you have x under deflection, so you are gonna have force k times x through, and one force F due to the friction, if it's moving in this direction, you're gonna apply the friction in the opposite direction. Make sense? If it's moving in this direction, the friction acting in the opposite direction of the motion. And it's acting right here at the contact point. Summation of the force would be m acceleration, mx double dot, is gonna be negative kx, negative f of friction. Good? And this friction is the reason of rotating of this cylinder. So how much would be the torque applied to the center of gravity? It's going to be the force times distance. This force is going to be in line with the center of gravity, which is this point. But this force has distance from the center of gravity. So summation of the torque would be J with respect to center of gravity times theta double dot, which is the angular acceleration of rotation, equals to force times R. Force, friction times the radius. It's gonna give me the torque. So now in these two equations, what I'm gonna do, I'm gonna replace in this equation FF by J with respect to center of gravity times theta double dot. So I'm gonna get mx double dot equals to negative kx plus negative J with respect to center of gravity times theta double dot. What would be the relation between x and theta? Theta would be x. For a small angle, it's going to be this. So we will get R theta double dot would be x double dot. So I'm going to replace x by r theta. So m r theta double dot negative k r theta, plus k r theta plus j center of gravity theta double dot equals to 0. It's gonna be m r plus j center of gravity times theta dot plus kr theta equals to 0. For cylinder, j with respect to center of gravity is going to be half of m r squared. Oh, I missed this r. I replace j cg theta double dot divided by r. So first I'm gonna multiply both sides by r. I'm getting m r squared plus divided by r. M plus j cg r squared times theta double dot plus k theta equals to 0. So this is going to be the equation of motion for this system. If I ask you what would be the natural frequency, angular frequency, it's going to be whatever the coefficient of theta, it's k divided by m plus j cg divided by r squared square root. And you can replace jcg by this one. Half of m r squared divided by r squared. You can cancel out these two. M plus half is going to be k divided by, or 2/3 of k over m. The angular frequency of this system is going to be 2/3 of k over m. Good. So for the homework or exam, you might be given by the system. You were asked to derive the equation of motion, either by using the Newton method. Sometimes applying this method is difficult, so you should use the energy method if you are allowed. If I have a damper here, you are not allowed to use the energy method because summation of potential energy plus kinetic energy is not going to be constant. Why? Because the damper is going to dissipate the energy over the time. So this summation over the time is not going to be constant. But for this system, you can use the energy method that I can show you shorter. So by using the energy method, so I said it's a pure rolling. So if this is the pure rolling, it means we have pure rotation about the center of rotation, which is this point. Pure rotation with respect to this point. So kinetic energy, if you have pure rotation, it's going to be half of J with respect to center of, if I call it O, with respect to center of rotation. Not center of gravity, center of rotation. Half of J naught theta dot square. This is the kinetic energy. Potential energy is only due to the spring, half of k x squared. Summation of these two, half of j naught theta dot squared plus half of k x squared is constant. One equation. The other equation is, we know that J with respect to center of rotation is J with respect to center of gravity plus mass times distance between these two, which is r squared. This is access theorem. So J with respect to center of gravity plus mv2, m distance squared. It's going to be the polar moment of inertia with respect to the other axis. So if I replace J naught by this, I'm going to get half of J center of gravity plus mr squared times theta dot squared plus half of k. X is r theta. X is r theta. We use over there. So x squared would be r squared x squared. And this is constant. So theta. This summation is constant. We can differentiate and set it equal to 0. So this is constant. I'm not going to differentiate this. I'm going to differentiate this part. So 2 times half is going to be 1. J center of gravity plus m r squared. Theta dot, derivative of theta dot with respect to time. Plus 2 times this is going to be 1. K r squared theta times d theta over dt equals to 0. Theta dot can be cancelled out by d theta over dt. So I'm going to get J with respect to center of gravity plus m r squared times theta double dot plus k r squared equals to 0. It's exactly same as this one. If you multiply both sides by r squared, you will get mr squared, J center of gravity, k r squared, which is this. Good. So again, you can use the equation, the energy method, when you don't have any dissipation of the energy. So if you are damper, you cannot use energy method. You have to use the Newton method. So now, suppose I'm going to add 1 damper here with the constant of C. In this equation, summation of the force. If it's moving in this direction, the spring is going to be extended. You are going to see the force in the opposite direction of deflection, which is left side. If it's moving in this direction, the velocity is going to be x dot, velocity of the center of gravity. So Cx dot is going to apply to this. And friction also is going to be in the opposite direction of motion. So summation of the force would be MA equals to negative Kx, negative FF, and negative Cx dot. Just one term is going to be added. For the torque equation is not going to change because these two forces passing through the center of gravity. They don't apply any torque about center of gravity. So I can replace FFR by JCG theta dot, theta double dot. So this equation is gonna look like this. M R theta double dot, X double dot can be replaced by theta double dot. X dot would be R theta dot, so plus CR theta dot equals to 0. So the equation is going to look like this. Just one term of CR theta double dot is going to be added. And again, if I ask you what would be the natural frequency of this system, still the natural frequency or angular frequency is gonna be the coefficient of theta, which is Kr, divided by this. Here we don't have this. So the coefficient of theta is K divided by coefficient of theta double dot, which is this guy. No matter we have damping or not, the angular frequency is always defined as coefficient of theta divided by coefficient of theta double, which is this. But equation of motion is different. And you cannot use the energy method for this new problem. Any question about this? One of the homework's problem is going to look like this, but different combination of the spring. For example, the spring is located at a different distance than this, so you should consider the torque for the spring force. But the approach would be the same. Any question before we move on next example? All right. This example was the exam problem last year or year before that. So the system was something like this. There was a bar, rigid bar, with the mass and polar momentum inertia. So the bar is not massless. Its center of gravity at the middle. So this is L over 4. This is L over 4. And this is L over 2. So the total length is L, its center of gravity. And here we had damping connected to this. This spring was 3K. This is a K. So So we were asked to find the natural frequency of the system. To find the natural frequency of the system, I have to find the equation of motion first. So even if I don't ask you to derive the equation of motion, you should find the equation of motion first. Since this system has a damper, you cannot use energy method. So how it's oscillating? If you move the bar from the relaxed position by the angle of theta naught and release that, it's gonna start oscillating. So we would like to find the equation of motion for that oscillation. Good? If this is O, center of gravity, if this angle is theta, I'm gonna draw the free body diagram for this part when it's at the angle of theta. Then I can write the Newton's equation and derive the equation of motion. So if this is at the angle of theta, this distance would be, how much would be this distance? How much would be the deflection on this spring? If we find that distance, it's going to be the deflection on the spring.
4 sine theta.
L over 4, which is this, times sine of theta. You will get this. So L over 4, and since theta is small, sine of theta would be can be approximated by the theta. So if this is the L over 4, the force applied to this point is going to be KL over 4 times theta. Why the force going up? Because we make the we extended the spring, so the force should be in the opposite direction of deflection. So it goes up. This distance is L over 4 times theta, but we are looking for a speed. Whatever is the speed of center of gravity, we can multiply by c and find the force applied to that. Good? So this distance is again L over 4 times theta. This is the x of center of gravity. But we are looking for velocity of that. So x dot of center of gravity would be L over 4 theta dot. So C L over 4 theta dot. What should be the direction of the force? Should it go up or down? The damper is acting against the motion. When it's going up, the damper should apply the force down. So this is how the damper is working. So the same logic for this spring. The length is L over 2 plus L over 4, 3L4. It's going to be compressed. Compressed means force should apply downward 3 L over 4 theta times K, 3K. Good. Now, everything is rotating about central rotation of O. So summation of the moment or torque about point O. This force times this distance is making clockwise. Clockwise meaning negative. So force times distance. Distance is L over 4. So summation of the torque would be negative K L over 4 theta times distance, which is L over 4 from this side. From this force times distance is again making clockwise. Force, which is CL over 4 theta dot times L over 4 distance, L over 4. And this force times this distance is making clockwise rotation, negative 3 LK over 4 theta times 3L over 4. And summation of the moment is always equals to polar moment of inertia with respect to center of rotation, which is O, times angular acceleration, second Newton's law for rotation. Good. The rest is just, we should simplify this. I have one term for theta, another term for theta there. I can add them up and move everything to the other side. I'm getting J naught theta double dot plus, this is gonna change to the plus, CL over 416 times theta dot, CL squared divided by 16 times theta dot, plus, this is going to be plus, this is going to change to plus. Here I'm going to get K L squared over 16 times theta. Right here I'm getting 9 L squared divided by 16 K. 9 here, 1 term here, 10. 10 L squared divided by 16 K theta equals to 0. This is gonna be the equation of motion. For a bar like this, with the length of L, J with respect to center of gravity is a 112 m L squared. 112 m L squared for a bar like this. So I can find J with respect to O equals to J with respect to center of gravity plus M times the distance squared. Distance is L over 4. It's going to be L over 4 squared. So half 1 over 12 ml squared plus ml squared divided by 16. I can add them up. 48, this command multiple between 12 and 16 is 48. This is going to be 4, this is going to be 3, 7 m L squared. So J with respect to center of rotation would be 7 m L squared divided by 48. So if I rewrite this equation again, 7 over 48 M L square theta double dot plus C L square divided by 60 theta dot plus 10 over 6 5 over 8 L square K theta equals to oh, I missed something here. This stiffness was 3K. Here, 1, 3 should be here. When I add it here, it's going to be 3. 3 plus 9 is going to be 12. 12 divided by 16. 3 over 4. They don't have the same stiffness. It's a 3K.
Why does that one have 3 on the other side?
Which equation? This one?
Yeah.
So why
No,
it has
why is there a 3 over there? And why
here? The force acting to this side is a stiffness times deflection. Deflection is L over 4. The force is going to be the stiffness times L over 4 times theta.
And when you did the compression on the other side, you did 3K as well on it?
No. This distance is L over 2 plus L over 4, which is going to be 3 L over 4.
Oh,
So this guy is going to be 3 L over 4 times theta. I multiplied by stiffness, I got the force. Now in this equation, if I ask you to find angular frequency, you should look at the coefficient of theta, which is 3 L square K divided by 4. You should look at coefficient of theta double dot, then cancel out the corresponding the term 48, 12. It's gonna be omega n would be 12 times 3 is gonna be 36. 36 over 7 K over L. (36 over 7 K over L). As you see, it doesn't matter what would be the length of the beam. The angular frequency is not dependent to the length of the beam. Any question on this? That was I think one of the exams problem last year or year before that. And on the homework, I think you have something like this to have more practice. All right, now we are ready to work on free vibration with damping. How can we find the response of the system when we have damping? we are gonna have some new definition, so make sure that you follow that and because it might be confusing. C. A spring constant is K. C is damping constant or damping coefficient. So the equation of motion for this, as we drive, it's gonna look like this. Mx double dot would be the force coming from the damper plus the force coming from the spring. And this summation must be equals to 0. It's an equation of motion. We would like to find the response of the system. It's a homogeneous equation because right hand side is 0. We assume that the solution is looks like so x, which is the solution, it's look like C e power st. C e power st. We are gonna plug in x dot and x dot in this equation and solve for s, and c is a function of initial condition. So if this is the x dot would be cs e power st, x double dot would be c s square e power st. So I'm gonna substitute plugging x double dot in this equation. I'm gonna get mc s square e power st plus this c is different than this. So let me look at this as this one. This is the damping constant. This is the coefficients for the solution. So MC would be C CS e power st plus K times C e power st equals to 0. This is x dot, this is x dot dot. I just plugged in the equation. Now, e power st, e power st, e power st, like with this coefficient c can be cancelled out from both sides. So what I will get is m s squared plus cs plus k equals to 0. It's a quadratic equation. I can solve for s. S1 and S2 would be negative coefficient of s plus and minus s square root of c squared minus 4k m divided by 2m. The quadratic equation has this root. Negative coefficient of s plus and minus s square root of this square minus 4 times this by this divided by 2 of coefficient of s square. So I'll divide c by 2m. It's going to be negative c over 2m plus and minus. If I move 2m inside the square root, it's going to be 2m squared. It's going to be c over 2m squared minus 4k over m. If 2m, I would like to move 2m inside the square root, it's going to be 4m squared. C has a squared, so it's going to be c divided by 2 and both are a squared. 4km divided by 4 m squared, so we don't have any 4. We are going to have k over m. So S1 and S2 are the value of the S such that they can satisfy the equation of motion. So C is given, K is given, M is given, we can find S1 and S2. So the general solution is going to be C1 e power S1t plus C2 e power S2t. So this is the general solution for this one of the system. Any questions so far? I'm going to define a couple of terms. So I define damping constant C or damping coefficient. Now I'm going to define critical damping constant or coefficient. I label that with CC, critical damping constant. So what would be the CC? Critical damping constant is the damping constant at which inside the square root is going to be 0. So if I set inside the square root equals to 0, I find the C value for this, and that value is called critical damping constant. Value of C at which square root of C over 2m square minus 4 over k over m equals to 0. So let me find that. C over 2m square minus k over m equals to 0. C squared divided by 4m squared would be k over m. I cancel out one of the m. C squared would be 4km. So CC would be square root of 4km. Good. So I'm just simplify this a little bit to write this square root of k 4k over m as a function of angular frequency. So you know that angular frequency is the square root of coefficient of x, which is k, divided by coefficient of x, which is m. So it's gonna be k over m squared. So cc is square root of 4k m. I multiply this by m squared divided by m squared. It's not gonna change. So m squared divided by m squared. So it's I'm gonna keep this 4k m divided by m squared multiplied by m squared. So this m squared can be, I can move it outside of the square root. It's going to be m square root of 4k over m. 4k over m. If I cancel out m squared with 1 m. So this 4 can come out of the square root. 2m square root of k over m. And this is omega m. So 2m omega m. So if the damping constant is equals to 2m omega n or square root of 4km, it's gonna make inside the square root equals to 0. And we call it critical damping constant. So I define damping constant, I define critical damping constant, I'm going to define damping ratio. Damping ratio or zeta. Damping ratio or zeta is defined as the ratio of C over Cc. Whatever is the damping constant is divided by the critical damping constant. We call it damping ratio. So on the roots for S that we could find, we had C over 2m. Now I'm going to simplify this C over 2m. C over 2m can be written as C over 2m times Cc over C divided by Cc. I multiply by Cc on the top. And here it's not going to change, but I can write as a C over Cc, C over Cc, multiplied by Cc divided by 2m. C over Cc as we defined is going to be damping ratio or zeta, and Cc divided by 2m. Cc is 2m omega n. So Cc divided by 2m is the angular frequency. So it's going to be zeta times omega n. Good. I'm just simplifying. S1 and S2 is going to change. Negative C over 2m, negative zeta times omega n plus and minus S square root of C over 2m is going to be zeta square omega n square minus K over m. K over m is omega n square. K over m is omega n square. I can take omega n out of the square root minus zeta omega n plus and minus omega n square root of zeta squared minus 1. And take omega n out of these two terms and have S1 and S2 equals to negative zeta plus and minus square root of zeta squared minus 1. The entire parentheses multiplied by omega n. So if I want to rewrite the response of the system is gonna look like this. X of t would be C1 e power S1t. S1t is negative zeta plus s square root of zeta squared minus 1 omega n times t plus C2 e power negative zeta minus s square root of zeta squared minus 1 omega n t. So from S1 and S2 we ended up to this so C1 e power that plus C2 e power negative zeta minus s square root of zeta squared minus 1 omega n t. The term 4 that I'm going to define is called damping natural frequency. It's just a definition, or WD. It's a definition. WD is s square root of 1 minus zeta squared times this. So WD would be s square root of 1 minus zeta squared times omega n. Now, here we have s square root of zeta squared minus 1. So if I change this to s square root of negative 1 multiplied by s square root of 1 minus zeta squared, this s square root of negative 1 can be written as I. So it's going to be I s square root of 1 minus zeta squared. Then when it's multiplied by omega n, it's going to change to omega d. So if I want to rewrite the response of the system, it's going to be C1 e power negative zeta plus I omega d t plus C2 e power negative zeta minus I omega dt. Based on this definition, square root of 1 minus zeta squared, 1 minus zeta squared times omega n is gonna be, I forgot this omega. It's gonna be omega b. What we need to do, we are gonna look at the different cases depending on the zeta. Depending on the zeta, we are gonna have the different cases of the response of the system. So next week we are gonna study that. I'm collecting the homeworks, and I think I already posted homework 4.
We have a test before.
No, the exam will be after the break.